Welcome back to the 10th video of this course on quantum processing. Today it's more about the quantum error correction. Last time we talked about the quantum coding and how classical coding is a bit different from quantum coding. And today we are going to face the errors and the noise that we normally have in our quantum channels. So let me just first say that we have what we call the operator measurement. This operator measurement is important to identify unitary evolution of the system by some eigenstates. This we correspond that for plus and minus u, the eigenvectors, the eigenstates here, and with some eigenvalues plus or minus 1. This is what we call the operator measurement that we are going to use to identify the error and to even correct what noise happens in the system. So let us begin with this quantum circuit. Okay, we have a quantum circuit that looks like this, and if I begin with the 0 and forget to do something here. If I begin with 0 and I trace it by Hadamard, so I put in a superposition state between the 0 and 1, so plus and minus. So 0 means plus. So, okay. And another operation, another system that is going to be inserted here that will unitary evolve over U, and with this controlled NOT gate, we will see what happens for this operation. So I have to measure and to know what the state, emerging state here at psi 0, and after some operation what's the emerging state here psi 1, and what's the emerging state after some Hadamard, again another Hadamard would be state psi 2, and finally the state evolution will have the result of psi. And by this measurement that we do over the environment for Z. Let's say Z. This is again the system environment model, but we model this by the quantum operation using the operation measurements that we have. So first begin with the psi 0. Psi 0 will be just here 1 over square root 2 superposition state. This is actually syndrome. This is just the two register. This is two quantum registers for two states. The two states that are multiplied like this. Okay, you have this state and this state. This by some Hadamard, and then after evolution, for the unitary evolution of the system, because we have this controlled NOT gate here, so we have this controlled operation. Remember that this controlled the C naught, and just remind you with the C naught, and the C naught is this matrix. 1 1, so 1 1 0 0 0 0 0 0 0 0 of here, and 1 and 1, so 0 and 0. Actually here is 1. Sorry. Okay. Here the 1 and here the off diagonal 1. This is a C naught. So when you apply that, you will find that you do nothing for the 0 state. So you will write it like this. Plus C1 for the eigenvectors here. For the other one, for the one case, you find that you just flip the sign. So flipping the sign is important for this circuit actually. Okay, so let's do the same thing that the psi 2 evolve after some Hadamard. That's actually the same, nothing will change. Okay, the same state here. If you combine this state and would like to write it in another more fashionable shape of this, you'll find that some cancels for 1, so eventually we'll have this kind of square root 2 of this 1, so 0 here, and another 0, just this 2, and this square root 2, this square root 2, and you will find that it looks like this. Let's say C0 0 U plus C1, and this one, and this is U minus. So this is the state after the evolution, and this is an important state that we will extract our eigenvectors that we can measure. We can importantly make sure that they correspond to our system here for 0 and 1, and we can conclude from here and say, okay, the operator measurements will be something like this. If I have this measurement for the z, which corresponds to 0, it will lead me to measure the basis, the psi, and this is the z. The psi will be kind of this, okay, for these eigenvectors. For 1, it will be the other eigenvector. So the operator measurements are just projectors in the plus and minus 1 eigenvalues for our system, for this system. Why is it important that we study those kind of operations? Those are just important for identifying the error and make sort of what we say error syndromes. We would like to define error syndromes that look like this. The error syndrome here is U1 is equivalent to the z, zi, that's just z, the operation, and U2, I, z, z. So let me tell you that we would like to apply these concepts on the results that we got before for this states, for these states. So let us just begin with the first one. So just take a look at these states, and then we come back again to this. So okay, so if I apply U1 over these 3 zeros, so it means that I have I, a projector, so just see that ZZI, so to begin Z is 0, tensor product with 0, 0, tensor product with I and 0. You will find that we're going to do nothing to the system, so the same bit operation, this kind of 2-qubit bit flip operation, but the same 3 zeros, the same for 1 actually, because 1 would do nothing again, or the operation would do nothing to this system. But it's more general to go into our come back here and try to calculate the syndrome operators. So for the first state, we saw that it's just the, so here say that, let's make it here Z1 and Z2. Okay, Z1 and Z2 just for U1 and U2. So if you apply the syndrome operators here, nothing happens, and here nothing happens. So nothing happens means that you have the +1 eigenstate, and the +1 eigenstate translates to the 0z. Okay, and for the same here. Applying, so we first recall that we have the kind of ZZI for the first one, which is the Z1. ZZI mean here I, nothing, and here Z. So it means that I flip because the eigenvalues, because of the eigenvalues -1 for projectors, and here for IZZ, nothing happens. For the case here that we have ZZI, so I does nothing here, Z would flip, so you would have kind of flipping, and the other one for Z2, you have IZZ, ZZ does nothing here, but you will flip, so 1, 1. For 001, you have IZZ, first ZZI for U1 and Z1, ZZI, I here does nothing, and here nothing happens. For the Z2, you have the ZZI, or sorry, IZZ, here IZZ does flipping, and here nothing happens, so yeah. And let's go to the other 4 cases here for the mutually orthogonal states that we talked about, and those are important, we will see. For the other case here that you kind of flipping, ZZI, nothing happens, so 0. And here is IZZ, you will flip. So for here, 101 for ZZI, you're okay. And here IZZ, you would flip. For 011, you have flipping, yeah, because of ZZI. But for IZZ, nothing happens. For the last case, for 111, means that you do nothing for the state, and the other IZZ will also do nothing to the state. So we have kind of fully got the operations for the syndrome operations that we have. If you look at those states and try to see, because we have 4 and other 4, those for the errors, okay? Now if I would like to make a second step for correction, for applying correction or recovery, so the recovery would mean that I have to get the, sorry, so recovery means that I have to apply some operations like the identity, it's like x123, 123 to the elements of the resulted elements for the operations to recover the state again. So if we took a look here, took a look at the another look here, that if I would like to recover the first, let's say that this is the batch number 1 and this is the batch number 2 for errors. The batch number 1 would, if you apply some, here you apply I, nothing. Let's say for 10 it's x1, and let's say for 11 is just the x2, and here the x3 for recovery operators. And for the other operators we will see, but the first batch of the operators will be that I have to apply that to identify my system for getting the same state. This is the recovery, okay, for the batch 1. But actually for the errors, okay, you will see that the second batch that we talked about for the errors, if you would like to apply some operators, the same operators for recovery, you're going to get the flipped state. So you won't get the same state, you will get the flipped state for the kind of digits that we have. So it means that this is not the right state, it's incorrect. So this is incorrect result. This is incorrect result. Now I'd like to say that for this kind of treatment we can map the goodness or the significance of the error correction procedures, that here it can tell me that okay, this is the wrong state, and let's get back to see how we can maybe reach the pure state again. And this is important actually for identifying the quantum error protocols and their purity or impurity, whatever. Okay, so let's just put some important definitions here. We have the fidelity. The fidelity is an important concept to learn, which is actually here. The fidelity of a state psi for the density matrix, okay, for their corresponding eigenvectors, that you take the square root of these overlap, the density matrix. This is actually the probability. If you look carefully, this is the probability. So it means that I take the probability of 1 minus the probability of error. If you would like to calculate the probability of error, here you find that this is p cubed and 3 states. So it's actually 1 minus p cubed plus 3 of p squared 1 minus p, right? It has to be larger than or equal in order to get the the nice fidelity that we are interested in. Here it means that I kind of maybe say 1 minus p cubed minus 3p squared plus 3p cubed, which is equivalent to 1 plus 2 p squared plus p cubed, and this is the, you take it to be like this. It's kind of what we have. And here means that I have the probability, it scales with the probability p-square. And as I said before, it's even more or much nicer than getting, because the other case I have just 1 minus p, it scales with p, the probability p, but now it's p square. And here it means that our quantum protocols are nice, and the quantum error correction makes more precision and more identification of the error for the fidelity state that we have here. Thanks a lot for watching, and see you in the next video.